Good morning. I'm very pleased to be having the opportunity to talk on mathematics and not only on organizational issues. So I'm going to talk about some work that we started with Mark Spivakowski and Javier Fernandez de Bobadilla some few years ago. And we extended this afterwards with my former student, PhD student from Brazil, Otoniel Nogueira da Silva. So this is on equisingularity problem. So the idea is the general idea of equisingularity, we're using what Mark already explained about what singularity is, so I suppose that we all have this in mind. So just think you have a family of spaces with some line of singular points that you are following. All these family of spaces have some singularities that you can follow. And you want to compare them to see how it varies when the parameter varies. So the idea is to check situation where the singularities are somehow the same. We need to fix what the same means. It could be topological, it could be from other point of view. So this is mainly the idea. And I will consider it mainly in the easy case of family of curves. So this starts with something like we have family of curves, long line, and we want to compare the singularities of these families, of these curves along that line. So the easiest case could be maybe family of plane curves living in C2, and to see this as a family, we see it with projection to C. We require this projection to be flat. I mean, in this case, it is. So the idea is to see the family of curves as fibers of that projection. So in case of family of curves, this has been probably the first point to be studied by Zariski, and things are understood, behave well, and we know that different point of view of equisingularity are equivalent. We have invariants. Maybe the most important invariant there is the Milnor number. This invariant helps to measure the singularity, the difference of singularity between curves. When I suggest to work on that, the idea is to work locally. So this is my space, and I am near the origin, and I am projecting to C, and I have mainly the special fiber, which is the inverse image of 0, and the generic fibers. The generic fibers will have the same behavior. The difference could arise at the special one. So measuring Milnor number of the generic fiber and the one of the special fiber, this allows us to say theorems for case of plane curves. So constancy of Milnor number is equivalent to the same topological type for these curves, is equivalent to something even stronger, which is having Whitney conditions of, in this case, there is nothing to say. We can say that the family of curves have the same multiplicity. Milnor number constant for plane curve singularities imply the multiplicity, Hilbert-Samuel multiplicity of the curve is constant. So this is the case of plane curves. Then one could generalize this setting. So there may be, keeping always curves in mind, one can consider a surface and the projection to C. Asking this projection to be flat means that the parameter here is not a zero divisor in the surface. So having this projection from a surface to C gives me fibers, which are curves, and we want to generalize what we know on the case of plane curves. So in nice cases, for example, when these curves are complete intersections, things still work again, and everything is known. We know how to deal with it. Even when the surface, when the family of curves here, let's say this is germ around 0, and I am going to C around 0, So the point is, how is the special curve, the special fiber, pi minus 1 of 0. So when this curve, pi minus 1 of 0, is reduced, still a lot of work is done. There is a very nice survey by Briançon, Granger, and Gallego that explain this case, family of reduced curves. And we know how it works. Things split. The equivalence that exists in case of plane curve singularity are not the same. Constancy of Milnor number, for example, does not imply constancy of the multiplicity. So we split into categories of equisingularity. We can ask for purely topological equisingularity, namely topological triviality. We can require something that is stronger after, which is Whitney conditions, mainly here, Whitney condition for the surface along the parameter axis. These are two different types of equisingularity. One is stronger than the other. And there is also a third one, generally called third one, which is related to Lefschetz behavior and equisaturation when one wants to look at it from the algebraic point of view. But still there is one case where up to recently nothing has been done, is when the fiber is not reduced. So my first objective today is to convince you that studying the case where the fiber is not reduced is not just the sake of algebraic nonsense. It's something that arises naturally. Looking to the cases where we have special fiber which has an embedded component is something more natural than one could expect. And once we include it, there are things to understand and others to be understood, and this is like this is a source of strange and interesting examples. So let me start with one easy example.
Non-reduced would mean that one of the irreducible components comes with a multiplicity, or as you said, with an embedded point.
Exactly. So what I will focus on an embedded point. So this is precisely where, what we did and what we are doing is work on family of generically reduced curves. Generically means that the generic point is reduced, but the special point, the particular point, the origin, could be fat point with an embedded component. Okay? So let's consider an example. This is parametrization. Let's call it P. From C2 to C4, given by UT goes to U3, U4, T, U5, T. Okay, so monomial parametrization. From C2 to C4, the image of P is a surface. And this surface can be seen as family of curves if I go by the projection to T. Okay? For each fiber, the curve is, the inverse image is a curve in my surface. This is flat morphism, not because there is no zero divisor in the image. We can check that the surface is irreducible, actually, and reduced. So the first thing to realize is that the parametrization of this surface does not induce the parametrization on each fiber. This is something very important, and I will convince you on that. So what is the S? The surface S has complicated equations. I have them written here, sorry. So consider the surface C4 with the coordinates X, Y, Z, and W. W is the last one, is the parameter here. So the equations of the surface are the natural one, X4 minus Y3. Then XZ minus Y square W. YZ minus X3W, and x2 y w2 minus z squared. So these are the equations of the equations of the image, and one can see naturally that if I take the ring of the surface and I cut by the parameter t, this is the ring of the special fiber. This is precisely C of x. Let me x, y, z, w. I mean w is 0 here. So I will get x4 minus y3, and then t goes to w go. So this is w, no? Here I'm checking the quotients with w. So w goes to 0, and then I get xz, yz, and z2. So this z2 gives me non-reduced structure of the curve, and the curve has fat point. I have an embedded component at the origin. If I consider only the parameterization given by u0, the image of u0 is just u3, u4. This is reduced curve which has exactly the reduced structure associated to this ring. Okay? So this is the first observation. You could still say, come on, but you have family of curves and consider the family of parameterization, and that's fine if everything works. Why one needs to look at it from the algebraic point of view and then find out that things do not work? The point is that if you look at these families as family of curves of parameterization, I have something that occurs. Let's take t different from 0. For t different from 0, the parameterization, the curve I'm looking at is u3, u4, t, u5, and that's all. This is the parameter of the curve. This is reduced curve, which is given by parameterization. I can compute its Milnor number, and its Milnor number in this case is, sorry, I make the computation quickly. So I will need to compute first the delta. For the delta, the one I am missing are u, u2, and that's all. u3, u4, and the rest are there. So delta is 2. So Milnor number is 4. If I take t equals 0, the parameterization is given by u3, u4, and in this case, the Milnor number is delta is 3, 6. Okay? So if I expect to look at it from the parameterization point of view, just having families of curve parameterized, which is wrong way to look at it, I'm trying to convince you, I will have curves with different Milnor number. The special curve has Milnor number higher than the original one. So this family, from the point of view of reduced curves, will not be topologically trivial, from what we know about families of reduced curves. But if you look at it from the point of view of the algebra and you consider the surface given by the parameterization, one can prove that the surface S obtained there satisfies is Whitney regular along the axis. The axis I'm talking about is 0, 0, 0, t. The axis of t is here. Okay? So surface that is Whitney regular along small stratum automatically satisfies topological triviality. So this point of view of thinking of families of parameterization is wrong. Doesn't work. We first need to consider the surface and take the projection, and this is the family of curves. Okay? And this family of curves has something strange. The surface obtained here is not Cohen-Macaulay. This is from those who like the algebraic point of view. So the special fiber has an embedded component. And then the general tools do not work. The Milnor number cannot be computed as we used to do. Okay, so this appears naturally. Even in nice cases, this is the image surface is Whitney regular along its singular locus. But spatial fiber has a reduced component, has an embedded component. Okay, so this is the first thing that occurs, and so it's natural to appear, and then we need to deal with it. And then one can construct strange and interesting examples. Maybe one famous example is one given by Javier Fernández de Bobadilla, which is the following. Consider the parameterization ut goes to u3, u4, ut, and u. So this is a family of non-singular curves. The generic one is non-singular. The special one is singular curve, is a cusp. But it has an embedded component. And he proved that this family is still topologically trivial. Things that do not happen in case of reduced curves. One hardly imagine how can this singular point allow topological triviality. Because we think in general in constancy of Milnor number. We have Milnor number of something smooth, which is 0, and Milnor number of something singular, which is strictly higher than 0 when it is reduced. So it doesn't work. And the key point, I mean, the proving that this is topologically trivial has been done just by constructing the product of the homomorphism that put the surface into product of the fiber with the axis. But then introducing invariants, one can understand what happens really there. So the situation for invariance is the following. If one consider just the curve with its non-reduced structure, there is no, I mean, the classical definition of Milnor number does not hold. For computing Milnor number, one needs the ring to be reduced. But it has been introduced by Brucker and Gröel. Brucker and Gröel introduced a new invariant that takes into account the depth of the embedded component. Taking into account this depth, they build a new delta invariant of the curve, which allows to construct Milnor number, and this Milnor number happens to work. So let me make it a little bit more precise. Consider now an ideal in C of x1, xn that defines a curve C. Okay, so this is the ideal defined in my curve, and suppose that C is generically reduced. What I recall, that's what I mean by generically reduced. The generic point is reduced, and there might be an embedded component at the origin. So we can measure the depth of that embedded component, which is, it is actually kind of homological invariant, but we can just show it, define it like this: the dimension of the radical of I divided by I. And this is finite dimensional vector space, and this is a way of measuring its depth. So he defined the delta of the curve C at the origin to be first the delta number of the reduced curve, let's do it like that, of the reduced curve at the origin minus epsilon, where C bar is the reduction of C. So what they claim is that they suggest as delta invariant, the delta of the reduced curve to which we subtract the depth of the embedded component. Okay? And then to show that, I mean, the main argument for them to define delta like this is the following theorem by Brucker and Greuel again. Saying that when you have a family, as in my case, so pi from x to c, family of generically reduced curves, then delta constant is equivalent to having what one calls equinormalization. So equinormalization means that the normalization of the surface induces a normalization on each fiber. This is somehow first step on equisingularity. You want the family of curves to have the same normalization induced by the normalization of the surface. Okay, this is weaker than topological triviality. So their new invariant carries the property known for reduced curve, constancy of delta invariant is equivalent to equinormalization. They succeed in carrying it into generically reduced curve. The following point is topological triviality, and then showing, defining then a new Milnor number just as mu of a curve C, even with generically with an embedded component, just 2 delta minus R plus. This is the famous formula where R is the number of branches. So if we extend the definition of Milnor number to generically reduced curve using the classical formula by Milnor, one would like to check if this Milnor number measures topological triviality. And the answer is yes, being careful. I mean, it's not yes in all situations. When the space X is not irreducible, some strange things could happen. Like the generic fiber could have different connected components. And this make things complicated. So this question was first worked by Lecontrine, was former student of Greuel. And then Greuel took it again and gave maybe the right statement. So let me state it just in some particular case. So this is by Lecontrine and Greuel, separately. No? Saying the following, that if X is irreducible, I'm simplifying the statement with this assumption. Then mu constant is equivalent to topological triviality. Okay, this is 2016. No, 17. So I'm not respecting the chronological order of what happened, but earlier, and maybe this was starting point of working into these aspects, our work with Javier Fernandez de Bobadilla and Mark Spivakowski and myself, we say the following. Consider again a surface S with a surface with one-dimensional, smooth, singular locus. It's always strange to say this sentence. Smooth singular locus. So S is Whitney regular. If and only if S satisfies Zariski discriminant criterion. Zariski discriminant criterion. What is this? These are two types of equisingularities criteria that hold for incomplete intersection. It was not known for non-complete intersection before that, and we extended to surface which could not be Cohen-Macaulay. So Zariski criterion is just the following. You take surface, you take generic projection to C2, generic projection to C2. It has a discriminant here. We require the discriminant to have a non-singular reduced locus. Okay? If you take the discriminant and you look at its reduced structure, then we expect it to be non-singular. So we proved using topological tool. We could not use invariance here because we didn't have Milnor number at that time. We proved this equivalence. And then afterwards, with Otoniel Nogueira da Silva, and myself, we extended the discussion to characterization of Whitney regularity in terms of invariant. So we proved that under the same assumption, Whitney conditions are equivalent to constancy of Milnor number and constancy of multiplicity. So here we started using the invariance introduced by Grohe and Brucker, even if this was quite older, but since we started using it later on. We proved that what is known for the case of reduced curves, that Whitney condition are equivalent to the constancy of Milnor number and multiplicity, still holds for the case of curves generically reduced with embedded points. And there are some other results and perspective for extending this to other criteria of equisingularity. So this is, I hope I succeeded in giving you some taste of saying that these embedded components have their own interests and arise naturally. This was my goal. Thank you.
Yeah, in this example that you wrote there, this U square, U cube, U5 times T,
U2, U square, or?
The one you wrote.
This one. Is it?
So if you put this in projective 3 space cross C, projective 3 space cross C, then you have a family of complete curves, no?
Yes.
A family of complete curves. And so this flatness condition means that the Hilbert polynomial is constant. So I mean, my question is geometrically, where does this embedded point come from? I mean, we are used that over the complex number, nothing appears from nowhere. Yeah, that this flatness condition, but then you say you have this family of curves which are reduced, and then you arrive that the t equals 0, and then
it is not reduced anymore.
It's not reduced. So my question is, where does this embedded component come from? Because Hilbert polynomial would say that if the Hilbert polynomial is constant, then this reduction changes the Hilbert polynomial because you're removing the point.
I think the problem is that we are considering the Hilbert polynomial of each parameterization. So you are thinking of the family of curves, like for each t we have a curve. So this is again thinking on family of parameterization. Family of parameterization does not correspond to, the global parameterization does not induce parameterization on each fiber.
Yeah, but
so
in this way, what I'm saying is that where does the embedded component come from?
From the image of the parameterization. If I take the image surface here, this surface is the one that has pathology. At least in non-projective case, that surface will not be Cohen-Macaulay. The image surface will not be Cohen-Macaulay, so automatically it has every section will have an embedded component. Whenever you have non-Cohen-Macaulay surface, every curve has an embedded component since it will, there is no regular sequence in the section. So I think this holds again still for projective surface. If I consider, if I consider the surface in C, in P3 times C, I expect the image to be still strange in that aspect. At least whenever we localize, it will be non-Cohen-Macaulay.
So the first coefficient of the polynomial is not affected by the it's only the constant term. The highest coefficient is not affected.
Okay. You're right. There was another question, I think. Sino?
If the discriminant process has some mild singularities, can you still say something?
In this example?
If you accept some singularities for the discriminant process, can you still say something?
If the discriminant locus is singular, it will not be Whitney regular. In some cases, no. There are things that could be said in terms of using this known Le-Groel formula and cutting the discriminant with some lines and pulling it back, and this could lead to measure something on Milnor number of the sections here and maybe understand topological triviality. This is not really done in the case of surfaces with non-Cohen-Macaulay structure. So there might be something interesting to do that there. We haven't done it, I haven't thought about it, but it could be interesting, you're right. Somehow of extending this Le-Groel formula to this situation, this setup. Yeah, interesting question. Thank you.
Questions?
Thank you.